Welcome all. So, today we will try to do 2 degrees of freedom system analysis. Earlier we have looked into the single degree of freedom system analysis. We will have a quick revision and then we will start the 2 degree of freedom system, okay, and analyze it with the structures and see its application upon different types of loading. Okay. So, let us start the things. Okay. Let us recap into the degrees of freedom. Okay. So, number of degrees of freedom, okay, that is the DOF, is the number of independent coordinates sufficient to describe the motion of a system completely, okay, and these are the coordinates sufficient to describe the motion of a system completely at any given instant. Okay. So, let us have a quick recap. Okay. So, the system shown here, okay, it needs only one independent coordinate, okay, that is only one degree of freedom to completely describe the motion. So, if we look into this system, okay, it can only translate in the horizontal direction. Okay. So, only one degree of freedom, okay, that is the horizontal translation, is required to completely describe the motion of this system at any given instant of time. Okay. Similarly, this parabola, okay, this pendulum, okay, follows this type of path. Okay. So, if we know the angle, okay, at any given instant of time, okay, we can chalk out the position of this system at any given instant of time. Okay. So, this system can be described by the one coordinate system, okay, the position of one coordinate at any given instant of time. Okay. Similarly, this system can also be described, its motion can be described at any given point of time by the knowledge of theta at any given instant of time. Okay. So, x of t or theta of t in this case. Okay. If we know this information, we know where the system is at any given point of time. Okay. So, these are called the single degree of freedom system. Okay. So, adding complexity to this system, okay, if two independent coordinates, okay, are required to know the position of the system at any given instant of time, then this type of systems are called 2 degrees of freedom. Okay. So, let us take this example below. Okay. So, it has two concentrated mass m1 and m2. Okay. So, to know the position of the mass m1, okay, we should know what is the position with respect to mass m1, and to know the position of mass m2, we have a different coordinate x2. Okay. So, in order to visualize the entire location of this combined mass system, okay, we should know the information of x1 and we should also know the information of x2 at any given instant of time. Okay. So, we should know the information regarding two independent coordinate systems. Okay. Here the motion of x1 is independent of the motion of x2. Okay. Similarly, if we look into this pendulum system, okay, this two pendulum system, then in order to know the position of this entire structure, okay, this entire assembly, we should know the location of the angle theta 1 and location of the angle theta 2. Okay. Since these two systems, okay, are combined by a spring, okay, if it had been combined by a rigid rod, okay, let us say that we replace this spring by a rigid rod, okay, then there exists a relationship between theta 1 and theta 2. Okay. Then these two coordinates, okay, theta 1 and theta 2, okay, they are not independent. Okay. So, that entire thing can be represented in terms of one coordinate system. Okay. Just if we have the knowledge of one coordinate, we can draw down the entire location of this system at any given point of time under the application of any given load. Okay. But since these are connected by a flexible spring, okay, then theta 1 and theta 2 becomes independent. Okay. And in order to know the entire position of this structure, okay, we should have the information of theta 1 and theta 2, okay, at any given point of time. Okay. So, this are called the 2 degrees of freedom system. Okay. Degrees of freedom, number of independent coordinates, okay, number of independent coordinates sufficient to describe the motion of a system completely at any given instant. Okay. So, we move ahead. Okay. The system that requires two independent coordinates to specify its motion at a given configuration at an instant is called a 2 degree of freedom system. Okay. So, it is a system, okay, and in order to specify its motion, okay, at any given instant of time, okay, it requires the help of two independent coordinates. Okay. So, this system is called 2 degree of freedom system. In a single degree of freedom system, only one coordinate is sufficient enough to specify, to know the position of the system at any given instant of time. Okay. Similarly, in a multi degree of freedom system, more than two independent coordinates are required to specify the motion of the structure at any given instant. Okay. So, 1 degree of freedom, 2 degree of freedom and multiple degree of freedom system. Okay. So, basically the requirement of the number of degrees of freedom, the number of independent degrees of freedom dictates what type of system we are dealing with. Okay. So, an example of a 2 degree of freedom system is a motor pump system. Okay. So, what happens in a motor pump system? Okay. So, this is a sketch of a motor pump system. Okay. In a motor pump system, okay, there is a base. Okay. The base is supported by spring. Okay. These springs are to isolate the vibrations of the system. Okay. So, there is a vertical displacement of the system. Okay. So, there is a vertical displacement of the system is able to move in the vertical direction, and the angular coordinate denotes the rotation of the mass about its CG, okay, making up two independent coordinates. Okay. So, what the system is able to do? The system is able to move in the vertical direction, okay, and it is also able to rotate. Okay. So, if we model the system like this, okay, then the system has a vertical motion and also the system is able to rotate about its centroidal axis, okay, it's about its center of gravity. Okay. So, since these two motions, okay, or these two independent coordinates are required in order to describe the motion of this system at any given instant of time, then this thing can be called as a 2 degree of freedom system. Okay. Now, one question arises. Okay. If you look into the figure closely, here actually we have written down 3 coordinates. Okay. X1 coordinates corresponding to the left end, okay, near the spring K1, and X2 coordinate near the right hand near the spring K2. Okay. And then there is a rotational motion about the CG of the system. Okay. So, now one can argue that we can call it as a 3 degree of freedom system or in general a multiple degree of freedom system. Okay. But as I told earlier, if you look closely into the system, this entire mass, okay, is a rigid mass. Okay. So, it means that there exists a relationship between x1 and x2. Okay. They are not independent. Okay. One can be described entirely in terms of another. Okay. So, x1 and x2 then boils down to one independent degree of freedom only. Though at a first glance it is looking like that there are 2 independent degrees of freedom, but since this thing is modeled as a rigid mass, okay, then they are related, they are not independent. So, 1 degree of freedom comes from the vertical motion x, where x1 and x2 are related, and then other one comes from the rotation of the system, okay, about its CG. Okay. So, there are only 2 degrees of freedom. Okay. So, whenever we are looking into any system, we have to find out how many independent degrees of freedoms are there. Okay. Not just at any location. Okay. Let us say in the same system, okay, we could have modeled it as multiple degree of freedom also. Okay. It might look like a multiple degree of freedom. Okay. Wherever there are spring, okay, we could have written the system as the spring locations, okay, at various positions, okay, K1, K2, K3, K4, K5, okay, and at each location we could have said that there exists 1 degree of freedom, x1, x2, x3, x4, x5. But if you look at this mass, okay, this is a rigid mass. Okay. So, in principle all x's are related. Okay. So, we need to know only one x, okay, in order to describe the motion of the other x. Okay. So, the independent system is only x1 here and the rotational. Okay. So, it boils down to a 2 degree of freedom system. Okay. So, this way we need to analyze the system, look into it carefully and find out the independent degrees of freedom required. Okay. And then consider it as a 1 degree of freedom system, 2 degree of freedom system, or a multiple degree of freedom system. Okay. Sometime it might also happen that we can analyze a problem using a single degree of freedom approximation also, a 2 degree of freedom approximation also, or a multiple degree of freedom approximation also. Depends upon the required parameters, depends upon also requires the degree of accuracy in the system. Okay. So, moving ahead. So, we are trying to give a general rule. Okay. So, the general thumb rule for the computation of the number of degrees of freedom, it can be stated as follows. Okay. The number of degrees of freedom of a system, okay, is the number of masses in the system, okay, times the number of possible types of motion of each mass. Okay. So, if we go back and look into the system, the entire mass can be tried to be concentrated here. Okay. And if we concentrate the entire mass, okay, so what this mass can do? It can move vertically up and down, okay, and this thing can also rotate. Okay. So, there is one concentrated mass which can move vertically up and down. So, 1 degree comes from here and it can rotate also. Okay. So, the second degree comes out to be here. Okay. Again going back to the previous examples. Okay. So, here also we have one mass, okay, and this mass can only move in the horizontal direction. So, 1 degree of freedom, okay, and there is one mass here and then it can rotate like this. Okay. So, one motion, one mass, one motion. So, 1 cross 1 will give me 1 degree of freedom. Here we have one mass, it can move in the horizontal direction. I have another mass, it can also move in the horizontal direction. These two motions are independent. So, 2 masses cross 1 motion for each of them. So, 2 degree of freedom. Okay. Similarly, for the system, 2 masses, okay, mass 1 and mass 2, and then both can rotate. Okay. So, 2 masses times 1 rotational motion for each of them. So, 2 degree of freedom system. Okay. So, this gives us a general rule, okay, of finding out the number of degrees of freedom for each mass. Okay. Now, let us try to look into this system. Okay. So, here what we can say, okay, the mass can be assumed to be concentrated in this part, okay, and it is inside a rigid frame. Okay. So, what it can do? There is mass, the entire thing can be considered as mass m. So, it can move in this direction, okay, the horizontal direction, and it can also move in the vertical direction. Okay. So, how many motions? Okay. So, there are 2 motions allowed. Okay. So, 1 mass into 2 motions. Okay. Again it becomes a 2 degree of freedom system. Okay. So, this is representation of a normal packing system. Okay. So, this is our device and here the stiffeners are used, okay, as a packing material. Okay. So, this becomes a representation of a 2 degree of freedom system. Okay. Some more examples of a 2 degree of freedom system. Okay. Same representation we can use. Okay. There is one mass, it can move in the horizontal direction. Okay. So, if we cut out this portion, okay, we go back to our old representation, okay, our old representation of the single degree of freedom system. Okay. So, here one mass, it can move in the horizontal direction. So, one mass into one motion, 1 degree of freedom system, and after that what we do is that we add one more spring in the vertical direction and one more damper in the vertical direction, okay, and then we allow the vertical motion also. So, one mass, one more direction, so 1 degree of freedom. So, in total we need 2 degrees of freedom, one in the horizontal direction and one in the vertical direction, which is shown out here. Okay. So, this becomes an example of a 2 degree of a freedom system. Okay. The lower figure, okay. In the lower figure we have mass m, okay. It can move in the horizontal direction. Okay. So, one mass, one motion. If we have another mass here, so one mass, again it can move in the horizontal direction. Okay. Both its motion, okay, are independent. Okay. So, total degrees of freedom is 2 degree of freedom. Okay. So, these are the some of the examples of a 2 degree of freedom system. Okay. So, moving ahead. So, now we are trying to look into the free vibration of an undamped system. Okay. So, before we do that, okay, let us give one more example, okay, of coming from an actual system to a approximation of a 2 degree of a freedom system. Let us take our example of our beam. Okay. If you remember in our beam, okay, okay, we approximated our beam as a single degree of freedom system. Okay. So, we represented this beam as an single degree of freedom system. Okay. K star, C star and M star. So, from coming from the real system to single degree of freedom system, how did we do it? Okay. We identified the mode shape. Okay. We argued that if, okay, so technically how many degrees of freedom are there? Okay. In order to describe the motion of this entire beam, okay, we need the information at each and every point. Okay. And they are all independent. So, there are infinite degrees of freedom. Okay. Now, we argued that the total motion of this system, okay, so the total, if you are looking into the vertical displacement y, okay, so the vertical displacement is a contribution from all the components. Okay. So, all the components we are summing up according to the different modes. Okay. So, the total value of y, okay, is a sum total of contribution from each of the individual modes. Okay. It means that there will be some contribution from the first mode. Okay. So, shape is phi 1 and this value will be q 1, then there will be a contribution from the second mode, okay, q 2, shape is phi 2 and so on and so forth, okay, q 3 and phi 3. Okay. So, all these modes, okay, all the infinite modes contribute to the final shape. Okay. So, this is the how we approximate the system. Okay. Now, we are arguing, okay, if there is a situation, okay, where we are interested in the displacement, let us say that we are interested in the maximum displacement. Okay. So, and the system is loaded uniformly. Okay. So, the system is loaded uniformly like this and we are interested in the maximum displacement. We can argue that the contribution of the first mode is maximum. Okay. So, maybe the first mode contributes 90% to the total displacement. Okay. If you are measuring the total displacement, the contribution of the first mode is 90% and the maximum displacement in this particular case is going to be occurred at the center. Okay. So, the center vertical deflection we choose as the degree of freedom. Okay. So, the shape is the first mode, okay, and the chosen degree of freedom is the vertical displacement at the center. Okay. So, using this theory we constructed our shape function. Shape function is the deflection equation, okay, mimicking this first mode or mimicking this particular mode, and the numerator is the deflection equation evaluated at this required degree of freedom. So, evaluated at y, the degree of freedom is y and this is evaluated at x equals to L over 2. Okay. So, this constitutes our shape function. Okay. And from this shape functions we calculated our equivalent mass, equivalent stiffness and equivalent damping, and we changed from the real life scenario into an approximate single degree of freedom system analysis. Okay. We can use the same analogy and analyze this system as a 2 degree of freedom system. Okay. So, what we need to do? Okay. So, let us say we have a case, okay, a situation comes, okay, where we need to find out the displacement at more than one juncture. Okay. So, there is a case where we need to find out the displacement at two locations, okay, y1 and y2, where y1 and y2 are located at certain distance from one of the end. It is located at a distance of x1 and x2 from one particular end. So, here and again the loading is uniform. Okay. So, here again we are saying that we are only taking the contribution of the first mode, okay, this particular mode. Okay. So, if we are taking the contribution of the first mode and our chosen degrees of freedom now are at two locations. Okay. We want to see what is the vertical displacement at these two locations y1 and y2. Okay. So, we again construct our phi function, okay, phi1 and phi2. Okay. So, if we do that, the deflection equation remains same, okay, because we are taking the first mode. Okay. So, first mode is mimicked by this deflection equation. So, the numerator remains same for the two shape functions, because the deflected shape is the same. Okay. In denominator, what we do is that we evaluate this deflection equation at for the vertical displacement and at x equals to x1, and this one we evaluated the deflection equation y2 at x equals to x2. Okay. So, this way we formulate our two shape functions, okay, and using these two shape functions we can calculate our two m stars. Okay. So, m1 star, m2 star, k1 star, k2 star, and so on and so forth. Okay. So, we can analyze this problem as a 2 degree of freedom system also. Okay. And if we require the information at more points, okay, we can keep on adding the required degrees of freedom. Okay. So, we can keep on adding the complexity of the system. Okay. So, in this way we can change a real life system to a single degree of freedom system, to a 2 degree of freedom system, or to a multiple degree of freedom system as the requirement might possess. Okay. So, similarly we are looking into a free vibration of an undamped system. Okay. So, we are modeling the simplest 2 degree freedom system. Okay. So, it has two masses, okay, and both mass can move in the horizontal directions, and those movements are independent of each other, okay, and they are separated out by two springs K1 and K3, and there is a spring in between K2. Okay. And we are assuming that x1 is greater than x2. Okay. So, now let us see how we can evaluate the free vibration of a system. Okay. So, in the free vibration of a single degree of freedom system, okay, what we did was we calculated the frequency of the system, okay, by what frequency this system is going to oscillate. Okay. So, omega 1 was k star over m star, okay, where m star and k star were given. Okay. So, this was the undamped natural frequency of the system. So, similarly we will try to evaluate the frequency of this particular system. Okay. So, let us start this thing. Okay. So, first of all what we need to do is that we will draw the free body diagram. Okay. So, what we will do is that we will cut out this system. Okay. We will separate out this system and write it down independently. Okay. So, we will take the system M1 out. Okay. We will take this system M1 out. Okay. And we will see how to write down the free body diagram of this system. Okay. And M1 is seeing a displacement of x1. Okay. And we are assuming x1 is greater than x2. Okay. So, M1. Okay. So, M1, this is having a displacement of x1. Okay. So, if we write it down using the D'Alembert's principle, the pseudo acceleration will be m1 x1 double dot. Okay. Now, what happens to k1? Okay. So, in this system, if this moves at a distance x1, okay, k1 will try to stretch at a distance of x1. So, the resisting force here will be k1 x1. Okay. So, this is being given out here. Okay. And now, let us see what happens to the other side. Okay. So, in the other side this system has moved x1. Okay. So, k2 tries to move this way, okay, and the resisting force will be k2 x1. Okay. Simultaneously also what has happened is that this system has moved this way. Okay. So, there will be a opposing force out here. Okay. So, K2 net displacement of the K2 will be x1 minus x2. Okay. So, K2 net displacement will be x1 minus x2, and we know that the spring force is based on the relative displacement. Okay. So, the net displacement of this system is x1 minus x2, and it will be exerted this way. Okay. So, spring resistance K1 x1 and K2 x1 minus x2. Okay. Similarly, we looked into the free body diagram of the other piece, free body diagram of this other piece. Okay. So, this is moving with a degree of freedom x2. So, the pseudo acceleration m2 x2 dot. Okay. We looked into K3 first. Okay. K3. So, this if this has moved x2, K3 will be opposing force like this. Okay. So, K3 x2 will be there. Okay. And if we can relate from this system, okay, if this is exerting force in this way, this will exert force in the other fashion. Okay. So, here we have drawn the free body diagram of the system. Okay. And then we write down the summation of the forces in the x direction. Okay, taking x as positive. Okay. And rearranging, okay, in terms of x1 and x2, we get this equation. Okay. Look here, the right side is 0. Okay. It means that we are dealing with a free vibration case. Okay. Simply meaning that there is no application of any external applied load. Okay. The system is going to oscillate due to any initial disturbance. Okay. Okay. And one thing also has to be kept in mind, if we look into these two equations. Okay. In both the equations, x1 and x2 are appearing together. Okay. It means that this is a coupled equation. Okay. As we have seen in case of damping also, we had coupled system and then we uncoupled it using the orthogonality principle. Okay. But right now we are having a coupled system. Okay. So, these are coupled equations of motions. Okay. So, these are called the coupled equations of the motions. Okay. So, for the normal mode of oscillation, each mass undergoes harmonic motion of the same frequency passing through the equilibrium position. What it means that each mass, okay, is going to oscillate around its mean position, okay, with a certain frequency. Okay. Since there are 2 degrees of freedom out here, okay, so there will be 2 frequencies associated with each motion. Okay. So, if we rearrange, okay, if we looked into the acceleration terms, okay, only x1 and x2 are there. Okay. So, we can write down the mass matrix in this form. Okay. And rearranging, we can write down the stiffness matrix in this form, and this is the forcing function. Okay. So, this is the mass matrix, okay, times the acceleration function plus the stiffness matrix, okay, times the displacement field, okay, equals to the forcing function, normally forcing function, which is 0 in this particular case. Okay. So, this is the free vibration equation. So, this is the free vibration equation of an undamped system. Okay. Free vibration means the forcing function is 0, undamped system means the damping is 0. Okay. So, undamped means damping is 0 and free vibration means the forcing function equals to 0. Okay. So, this is the simplest case. Okay. Okay. So, we are assuming a harmonic solution for this particular equation. Okay. So, x1 and x2, we assume that this is represented by an harmonic motion. Okay. So, this is the assumed solution, okay, assuming a harmonic response. Okay. This is similar to what we did for the single degree of freedom system. In a single degree of freedom system, we assumed the harmonic motion. So, our solution was a sin omega t plus b cos omega t. Okay. So, this was the assumption of our harmonic solution. Here we are also doing the same thing. Okay. Then we represent the acceleration in this fashion and we substitute this into the our equation of motion. Okay. So, only unknowns are a1 and a2. Okay. And this is our equation, okay, multiplied by a1 and a2 equals to 0. Okay. So, for a non-trivial solution, this matrix should be, the det of this matrix should be 0. Okay. So, we evaluate the determinant of this matrix, okay, the matrix Q. Okay. So, the det of matrix Q should be 0 for a non-trivial solution, okay, because a1 and a2, if they are 0, then there will be no motion. Okay. So, we assume that the det of this matrix is 0. Okay. So, solving for this, okay, we got the solution for omega, okay, and the roots of this equation are given by this equation. Okay. So, this omega are called the natural frequencies of the system. So, omega 1, whichever is the lowest one, is called the first natural frequency, omega 2 is called the second natural frequency. Okay. It means that the first system is going to, where we assume the x1 degree of freedom, it is going to vibrate with frequency omega 1 and the other one is going to vibrate with the frequency of omega 2. Okay. So, here what we have done is that we have seen our 2 degree of freedom approximation. We had a quick recap about the first degree of freedom approximation and we also saw how to change a real life system from a multi degree of freedom system to a single degree of freedom system and again subsequently to a 2 degree of freedom system. This can also be extended to the formulation for a multiple degree of freedom system. Then we took the 2 degree of freedom system, an undamped system, and then we evaluated the frequency of the system. We first formulated the equation of the motion, then we did the matrix manipulation and we evaluated the corresponding frequencies of the system. So, we will stop here. Thank you.